All right. We will start now with chapter 18, which is Introduction to Network Layer. And as always, comments are on. Uh, if I said anything wrong and you want to correct me or you want to add any information, feel free to add it in the comment section. And as always, all credits goes for the KFUPM University for these slides, so the slides won't be shared. The outline is network layer services, packet switching, network layer performance, IPv4 addresses, and forwarding of IP packets. Uh, Network layer services. The internet is made of many networks or links connected through connecting devices. In other words, the internet is an internetwork, a combination of LANs and WANs. Uh, so we have two concepts for this packetization and routing and forwarding. Packetizing, the first duty for the network layer is packetizing. It's encapsulate the payload in the network layer packets at the source and decapsulate uh, at uh, at the destination. Payloads from the network layer at the destination. In other words, one duty of the network layer is to carry a payload from the source to the destination without changing it or using it. The network layer is doing the services of carrying, such as postal office, which is responsible for delivering packages from a sender to a receiver without changing or using the contents. And also the routers are not allowed to decapsulate the packets they received unless the packets need to be fragmented. The routers, the routes are not allowed to change. The routers are not allowed to change. Uh, Not allowed to change source and destination addresses. The same figure for each layer that we will take. Routing and forwarding. Routing, the network layer is responsible for routing the packets from its source to the destination. This means there is more than one route from the source to the destination. The network is responsible for finding the best route among all these possible routes. The network layer needs to have some specific strategies for defining the best route, which we'll call routing protocols. Forwarding we can be defined as the action applied by each router when a packet arrives at one of its interfaces. Uh, the routing action is done by the decision-making table, sometimes called the forwarding table, and sometimes the routing table. When a router receives a packet, it needs to forward the packet to another network in unicast routing, or some networks a multicast routing. So either it's one or many. To make this decision, the router uses the destination address to find the corresponding output interface number in the forwarding table. It is an example of a forwarding table. The data wants to be transmitted through the router. The router says, "Oh, if I have the forwarding value is B, then the interface will be 2, so it will go from here." Maybe other one, if it was A, it will be from 1. Maybe other one will be C and 3. It will go here and so on. This is the concept of the forwarding table. Like each value corresponds to an output interface. Packet switching, communication networks. We have switch network consists of circuit switch and packet switching, and also we have a broadcast network. And nodes share a common channel, so common channel nodes send to one on or more end nodes. Packet switching, we have routing. Refers to the network wide process that determines end-to-end paths that packets take from source to destination. Forward refers to the router local action that transfer packets from an input to a write output link interface. In the network layer, a router is a switch that creates connection between an input port and an output port or a set of output ports. Only packet switching is used at the network layer. So packet switching only used at the network layer because the unit of the data is layer is a packet. Circuit switch is mostly used in the physical layer. So physical layer we use the circuit switch, but for packet switching we will use it only with the network layer. Today a packet switch network can use two different approaches: the datagram approach, the virtual circuit approach. When it's the first one is connectionless, the second is connection oriented. Uh, Datagram approach, connectionless service. When the internet is started to make simple and network layer was designed to provide a connectionless service. Each packet is treated independently, uh, only responsible for delivering of packets from the source to the destination. The packets in a message may or may not travel the same path to their destination. So here is a figure to show a connectionless datagram. Uh, the From the sender, the packets are sent randomly, like each one go from different paths. Uh, but then on the receiver side, show out of order. It receives out of order, but it's the receiver job to order it by sequence numbers and so on. But the same concept here with like here it shows is the routers based on the forwarding table in a router when used in connectionless network. But here the virtual circuit approach, connection oriented service, also called, is a relationship between all packets. Uh, a virtual connection should be set up to define the path for the datagrams. This type of server not only must be packets contain the source and destination address, it must also contain a flow label, a virtual circuit identifier that defines the virtual path the packet should follow. So here is, for example, data sends an order uh, and with the same path because it's a connection oriented. And here the receiver do not have to order anything. Here is the forwarding table for the connection for the virtual circuits network. We have the port, we have the label for the incoming and outgoing. So here is the incoming, here is the outgoing. It's one of the interfaces. Connection oriented phases. Uh, the connection oriented phases is the first one is setup, then data transfer, then tear down, which means terminate all the or destroy all the forwarding table that has been created. In the setup phase, the source and destination address of the sender and receiver are used to make table entries for the connection oriented. So each router will make his own forwarding table. Then in the data transfer mode or phase, each packets will be traveled in different paths or in one path. Then the tear down phase is the till the source and destination to delete the corresponding entries or the forwarding tables. The transfers occurs between these two phases. Yes. So here we can say you can assume that the label is any random number that you want to choose. So here we pick the label, incoming label 1, we'll make it for 14. Then the outgoing port will be 3, so it will go from this way till the R3. Then we will label it by 66. Now randomly, just pick any number. Then we will forward it to, it says that port 3, it will go from port 3 to the R4, the router 4. Uh, then we label it by 22, and here it says that it will go for port 4, the interface 4, so it will go to the destination. Now, after it's reached to the destination, this is the first step, which means the setup step. We just take labels and we follow the port or the interface that has been decided already, and we will just put labels. This is the first step, is the setup. We're still in the setup phase here. We will pick also random label for the destination. Let's say it's 77. Then we will go back like port 1. We will go using the label 22 that we have picked already, then to port 3. Here's the port 3. Then we will go for port 1 with label 66, and then we will reach here port 1, and it will be reached to port 3. This rise with label 66. Then the label will be 44, and it will be through the interface 1, and it will go to uh, the sender side. This is all in the setup phase. Now we want to the second phase, which is data transfer. Assume we have the data, the source is A, the destination is B. Okay. Then the starting point is the label 14, and it will go to port 1. Then the outgoing will be from interface 3, and with the label 66. Label 66, interface 3. Then it will come here. It says it will go from port 3 or interface 3 with the label 22. Then it will come here with the label 122, right? Then it will go to interface 4 or port 4 with the label 77, and it will reach the destination, which is computer B. So this is for part 1. Now with part 2, network layer performance and IPv address forwarding of IP packets. So the performance of a network can be measured measured in terms of delay, throughput, and packet loss. Congestion control is an issue that can improve performance. Okay. We have 4 types of delay: transmission delay, propagation delay, processing delay, queuing delay. So transmission delay is that a sender needs to put the bits in the packets of the line one by one. If the first bit of the packet is put on the line at time t1, and the last bit is put on the line at time t1, the transmission delay will be the subtraction between the two. The subtraction between the two. Okay. The transmission delay will be the subtraction between the two. So the transmission delay differ from depending on the packet size. So in other words, to calculate the delay of the transmission delay, we will need to have the packet length and the transmission rate. As given in an example, we have given the packet length, which is 10,000, and we have given the transmission rate, which is 100 million. So we do the math, and then you will have 100 microseconds, I guess. So this is for the transmission delay. The propagation delay is the time it takes for a bit to travel from point A to point B in the transmission medium. So the propagation delay usually depends on the propagation speed and the distance. So we have the formula, the distance over the propagation speed. And here we have an example. The distance is 2,000 meters, and the propagation speed is 2 multiplied by 10 to the power 8. We will divide this by this. We will have 10 microseconds, and this is how we can have the propagation delay. Processing delay, it's the time required for a router or a destination host to receive a packet from its input port, remove the header, perform an error detection procedure, deliver the packet to the output port, and so on. So it do many things just to process the packets that have been received. So it's just not receiving the packets, it got many processes. So we don't have actually a formula, an explicit formula for it. So they created this formula. It's the time required to process a packet in a router or a destination host. So you can say it's calculated as average, the average of set of packets or something. So you can say the delay of the processes is the time required to process a packet in general, to do all of these steps for a packet. queue delay. It's happen normally in a router, in an input queue, an output queue. So the queuing delay is measured as the time a packet waits in an input queue and output queue of a router. As we say, as we discussed here, what was in the first part, like when we was in the router, at which we was in interface 1, for example, and going to interface number 3, we want to calculate the delay in the input or the interface, the first interface, and the output interface, or the output node. These are calling queue delay, and also it got no explicit formula. So the time a packet waits in an input and output queue in a router, and we have a total delay. The total delay of all of them will be n plus 1 for the delay for transmission, propagation, and processing, uh, and plus n multiplied by delay of q, because uh, n plus 1 transmission delay at each one of them. But for the q, we don't need plus 1, just the n related to n routers. Propagation delay related to 1 links, and this n, and also destination to the n, and the source. Okay, so the first one, the transmission, deals with the source plus the intermediate routers. Here we have n plus 1 links, and here we deals processing delay. It deals with the n routers and plus the destination. But for the queuing, just normal router, so it's just it will be n only. So this is how to calculate the total delay. I hope it's clear. Okay. Now with the throughput. The throughput at any point is a network defined as the number of bits passing through the point in a second. Okay. We can call it a transmission rate. And we just, if we want to calculate the throughput, just taking the minimum between all of the medium. So here we have 100 kilobytes per second, here 200, here 150. So the throughput will be 100, the minimum. Okay. Like here, for example, he says the example, like this one has 100 and this 40. So what's the throughput? It will be 40. The throughput will be 40. And here another example. Here it's considered only he said we have 600 in the main link, kilobytes per second in the main link. And he focused only on the sender size. So you have 200 for each one of them. So the throughput will be 200 if he only considers the source part. If he considers the source and the destination, it will be 100, because 600 divided by 6 devices, 100 each. But in this example, he's only considering the source throughput, so it will be 200, because it's the minimum. All of them are 200, so just take one of them. Packet loss is the number of packets lost during transmission. Received packet while processing another packet, buffer waiting. Yeah, I just read the concept, but generally this is a concept. Number of packets lost during the transmission. Here we have a graph for throughput and delay. Both of them, like here, delay deal with capacity. The difference is one with the throughput and the other with the delay. The difference, you can say, like the delay keep going exponentially. Okay. But the throughput, it will go like this until it reaches to the no congestion area, then it goes down. So delay as a function of load, just know the graph for it. Try to understand it or memorize it. Okay. A back pressure back pressure technique can be only used in the virtual circuit network. It's simply like when we have cognition, it just tell the previous router uh, about the congestion, and it will keep going until it reaches to the source. Okay, it's a connection control mechanism in which a congestion node stop receiving data from the immediate upstream's node or node. Backup pressure is a node-to-node congestion control that starts with a node and propagates in the opposite direction of the data flow to the source. Yes. And the shock packet, simply instead of going one by one to each node, it just whenever there is a congestion, it will just take a packets called shock packets, and it will uh, make it reach to the source, and that's it. This is the difference here: node to node, and here from the congestion to the source immediately. Shock packet, the warning from router. Yeah, okay. The third part is of chapter 18, IPv4 addresses. The identifier used in the IP network layer is called the internet address or IP address. IPv4 is a 32-bit address, is uh, uniquely and universally defines the connection of a host of a router to the router to the internet. The IP address is the addresses of the connection, not the host. So it's address of the connection, not the host or the router, because if the device is moved to another network, the IP address may be changed. So it depends on the internet that you are connecting to. If a device has two connections to the internet via two networks, it has two IPv4 addresses. So the address space, the address space of IPv4 uses 32-bit addresses, which means 2 to the power 32. If there is no restrictions, more than 4 billion devices could be connected to the internet. Uh, Here is how they usually represent the IP address in binary format or in dotted decimal. This is the most common way, or in the hexadecimal. Okay. Okay. Hierarchy in addressing. As we said, it's the 32 bits. You can say that the prefix shows us which network are we dealing with, and the suffix defines the connection to the node, to the device itself. A prefix can be fixed or fixed length or variable length. IPv4 was first designed as fixed length. Then they saw it's weak or something like this. So they made another thing called classless addressing, which is the variable length. Uses the variable length network as a prefix. Yes. So the classful addressing, the one that has the constant prefix. When the internet started, so the fixed lengths are first one 8, 16, 24, and they are divided to 5 classes: A, B, C, D, and E. The schema is referred as classful addressing. So here is more explanation about it. Like here, he is saying class A, the length of it is 8, as we see, the first one 8. But since the first bit, which is 0, defines the class, we can have only 7 bits. So the first bit when representing a binary is 0. So it has no use. We use it to identify this class. So the number of networks that we can have is 2 to the power 7. And in class B, it's 16 bits, as mentioned here. But we need two bits to identify it, which is 1, 0. So the total networks we will have, it's 2 to the power 14. And the same for class C. It's 24 bits, but we are using 3 bits to identify it, so it will be 2 to the power 21 networks that we can use in the class C. And here is more explaining the each one of them is 8 bit, 8 bit, 8 bit, 8 bit. Class A need only 0. Class B need 1 0 to so that we can identify it. Class C need 1 1 0. Class D need 1 1 1 1 0. And class E 4 ones in order to identify it. Here is an example. Find the class of the following IP addresses. Okay, the first one, since it's 0 0, there is nothing called 0 0, but there is 0, so it will be class A. The second is 1 1, so 1 1 then 0. Okay, then it will be C. Yes. Or you can identify it as a decimal. You can memorize it like from 0 to 127 is class A, and so on for the rest of the classes. And here is another example when it gives as dotted decimal, which is the most common way to represent the IP. Since the first one is 158, it lies in the second class, so it will be class B. Or 227, it will be class 227, it will be class D. All right, or you can convert the decimal to binary and keep unstuck with this binary representation of the classes. Here it shows you the addresses, like the first class is reserving 50%, and the second class is 25, then 12%, then 6%, and so on. Here is the prefixes that we have discussed. Yeah, nothing new. Just take a look at it. Address deliberation. The reason that class-full addressing has become uh, obsolete is address depletion, which means that we're not distributed properly, so addresses being rapidly used up, resulting in no more addresses available for the organization and individuals that needed to be connected to the internet. The concept of address mask is a 32-bit number in which the in leftmost bits are set to ones and the rest of the bits are set to 0. In order to know the first address, the last address, we will know more about it. Uh, there is actually a mistake here, I guess. It should be 2 to the power 32 minus n in the exponential, not in beside it, okay? So it will be like this, I guess. 2 to the power 32 minus n. Hey, I hope you got the idea. 32 minus n. Ah, that's bad. 32 minus n, then minus 1, okay? So, default mask. Class A default start with the 255. Class B, the first two. Class C, the first three. That's it. And operation. It's like depending on the and operation, like if there is two ones in the binary, 1 and 1, the resulting will be 1. If there is 0 and 1, the resulting will be 0. If there is 0 and 0, the resulting will be 0. This is the AND operation between the two binaries. The mask concept, AND operation, the net ID, network portion is the net ID. Host portion is the host ID. So here is for example, if you convert this to the binary and convert this to the binary, and you did the AND operation, so whenever you find two ones, the result will be 1. Whenever you find two zero, the result is 0. Whenever you find 1 and 0, the result will be 0. You will get this IP address. So it's an AND operation, normal AND operation between two binaries. So it will retain the net ID of the block and sets the host ID to 0. The net ID is the network portion, and the host ID is the host portion. Classless, which is the variable length, requires that the length of the IP address also be increased, which means the format of the IP packets need to be changed. The short-term solution still uses IPv4 addresses, but it is called classless addressing, which is the variable length, as we said. So here, the slash notation, the concept of slash notations, we mean by this slash and then n, and the n can vary. We decide which n to use or which n is given in the question and so on. So it's not constant, as we saw like previously 8 and 16 and so on. Extracting information from the address. Okay. Given any address in the block, we normally like to know 3 pieces of information. The number of addresses, which will be 2 to the power, and the number of the valid host addresses. It will be number of addresses minus 2, the first addresses in the block, and the last addresses. So we will use the concept of the mask, okay, 32 minus n. The concept says if you want to find the first address, keep the the rightmost bits all to 0. If you want to find the last address, keep all the rightmost bits to 1. Set them to 1. And if you want to know the number of addresses, 2 to the power 32 minus n. Here is an example. We have the slash notation, which is the prefix here. We have 27. Number of addresses, 2 to the power 32 minus 27, which is the number we have here. The total is 32 addresses. If he asked you what are the number of valid host addresses, you will subtract 2 from this number. You will get the valid host addresses. Now, how to find the first address? You will convert all of these to the binary and leave the first 27, one of them, unchanged. Then the remaining, convert them to zeros, and you will get the first address. Same thing with the last address, but instead of converting them to zeros, convert them to 1, and you will get the last address. What if this was 25? You will keep the first 25 bit unchanged, then you will change the remaining to 0 to get the first address, the 1 to get the last address. What if it was 20? You will keep the first 20 bits unchanged, and you will change the remaining to 0 to get the first address, or to 1 to get the last address, and so on. And this for part 3. Now with part 4, we discussed this. Okay, in classless addressing, here just explaining what he's not doing anything. Yeah, he explained like here, for example, it's point-to-point link. Okay. Here's it shows you how like the address can be distributed differently according to the prefix and so on. Last one is point-to-points, like from 56 to 57 and so on. But here it's more than one address, like from 00 to 255 so it's a big 255 addresses or something, and so on. Just so you go, the concept of the variable variable length prefix, like each prefix, when you change it, it will have different block and so on, different range of block and so on. Yeah. Here he's asking you like, if I have a block of 1000 address, what is the number of addresses need? So to get the number, the prefix links. Oh, he's asking for a prefix link. So first of all, he gave you 1000 address, okay? But 1000 is not multiple of 2. It's not multiple of power of 2. So convert to the nearest power of 2 and increase it. Like Go up, don't go down. Okay, go up the 1000, not down it, not below it. So the nearest one that above the 1000 and it's a power of 2 is 1024. Now he's asking you to get the prefix. To get the prefix, we have a formula: 32 minus log 2 of the address, the number of address that they gave you, but make it to the power of 2. Okay, he get 22, so the prefix is 22. That's it to get the prefix. Yes. Okay, that's it for part 4. Last part, which is part 5. We discussed this, okay. Subnetting. Here, he give you like an organization or this thing, and he says, "Oh, I want to distribute it among different subblocks and so on." So he give you the address, he give you the prefix, he give you everything, and he said, "Oh, I want one subblock of 10 address, one subblock of 60 address, one subblock of 120 address." So first of all, they are not multiple of 2 or not multiple of not a power not a power of 2. So we will convert them to the nearest power of 2 possible. Like I guess this will be 64 and this and so on. But first of all, let's see how the number of addresses that we have. We have the prefix 24. So to get all the number of addresses, it will be 2 to the power 32 minus 24. It will be 256 addresses. If he asks you what are the number of valid addresses, you will say 256 minus 2. So the answer will be 254 valid addresses. And the first block will be this. Last Okay, first block will be this. Last block will be this. How to get the first block and the last block? Convert this to the binary and keep the first 24 bits unchanged. Then the remaining bits, change them to 0. You will get the first address. So same thing for the last address. You will convert all of this to binary. You will keep the first 24 bits unchanged. Then the remaining bits, you will change them to 1 and you will get this last address. So we know the first address, we know the last address, we know how many valid addresses, we know the total addresses. We have the sub blocks that the organization trying to divide. We will start the first one. Always start with the biggest sub block that is given in the question. So here is it's 120. So it's not the power of 2. So we'll make it 128, like because it's not power of 2. Okay, after that we want to know the prefix of it, of this sub block. Okay, so we will use the formula 32 minus log 2 of the 128. We will get 25. So uh, the prefix will be 25 for this block. Now we want to know the first block and the second where is it? Yes, the first address and the last address. What are we going to do? Same thing. Take this address that is giving the question, okay? But now, not the prefix, not 24, it's 25. So you will change all of this to binary. You will make the first 25 bits unchanged. Then the last bits, or the bits are remaining, make them 0. You will get the first address, which is this, okay? Then same thing. Convert this. Convert this to binary and make the first 25 unchanged, then the remaining change them to 1, all of them, then you will get the last address. So here if you count from 0 to 127, we have 128 addresses as we get. Okay, now go to the second biggest sub block that are given, which is 60. It's not power of 2, so make it 64. Then use the formula 32 minus log 2 of 64. You will get 26. So the prefix will be 26. Now take the same thing, first 26 unchanged, then change the rest to the 0. You will get the first one, the first block. Then make the same for the last. Do not change the first 26 bits. Then the remaining change them to 1. And then you will get the last address of this subblock. Same thing with the last block, 16. Using the formula, we know the prefix converted to binary. Uh, It's the original. The one that you are going to convert is the original IP that is given. Okay. Then do not change the first 28 bits. Change the remaining to 0. You will get the first one. Then you will get the last one if you change them to 1. Now, it will be from 192 till 207, which is 16 address. Now, if you add all the previous addresses, you will have that we have 208 addresses, which means there are 48 addresses are left in reserve, so it's not unused. Okay, we did not use it. The first address in the range for the unused, the last address of the unused. We don't know about the prefix length yet because it's not given the question. Okay, so how did he know that we have 48 addresses left? He said that we said at the beginning we have 256 address. Okay, and at the end we saw like we have 208 addresses. Okay, just see the last address and add to it a one. You will know the number of addresses, which is 208 addresses that has been used. Now subtract 256 from 208, you will get 48 addresses are left unused. It will be from 208 till the 255 without a prefix because we don't have it, we didn't know it. So that's it for this part. Here is an illustration as a figure for the things that we did previously, the subblocks. Okay. Address aggregation. It means like combining all of these addresses as a one thing. Okay, like from the first one to the last one. Okay, so the ISP combines these 4 blocks into one single block. Should be sent to the ISP. The ISP is to forward the packets to the appropriate organization. Similar to routing, we find the postal network first to the capital and so on. Dynamic host configuration, DHCP. Dynamic host configuration protocol. It's assign what? Manually assign addresses. So instead of manually assigning addresses, DHCP will assign. We will assign addresses to all of the computers that are in an organization or something. So DHCP is an application layer program. It uses the client server paradigm that helps the TCP/IP at the network layer. So addresses segments as an can be done automatically instead of manually via DHCP. You have the message format for it. Take a look at it. It's 32 bits. He's explaining here all of its options and so on. You can take a look at it. And one thing of it, it's the option format. Where is it? Option format. Yes. Where is it? Code. I don't know. So this maybe you will need to know this: the discover and the offer and the request and the acknowledge. These are the most well-known format. You can see it here. The client got nothing, got no client address, no your address, no server address, nothing. So by default, it will have the destination address like this, and it will discover. It will ask a server to offer them anything. So it will use DHB discover. So it's use the first one. The value will be 1. Then the server is offering, so it's using the value 2 to offer of him an address or the server and also source address. Then it's updated in the client. Then he will request now something. So he's using the third value. Then the server will acknowledge. Then he will use the 5th value. Yes. So the DHCP, it's just giving a client an address and make them know the server address and so on. The NAT, network address translation, it's just a mapping between the private and the universal address. Set of global internet addresses for communication with the rest of the world, like this. Here's a private organization. So whenever I want to communicate with the outer world, I used a global IP that is different from the internal IP. So here each one of them have an IP, then it will be an aggregation as one IP somehow. But instead of using this private IP that we don't want anyone to see it, we use the NAT concept to make a global public IP and talk with the rest of the world by it. Okay, here is explaining the concept. This is the IP, but he's taking different IP, and after he finish, he come back with the data with the same IP. Then the NAT will translate or change the public ID to the private ID of the organization. And here is the same example. Let's take, you can memorize it as the source here and destination are reversed here. Okay, and same thing here. The source and destination are reversed here. I memorize it like this, but the concept is that it's using the translation table. Uh, so whenever it goes outside the organization, it's use different source IP, but the destination remain the same. And whenever it comes to the private receiver, also it will change the destination IP to make sure it's private. So it uses different IP to communicate with the outer world. Okay, this is simply the concept. The translation table consists of private address, private port, external address, external bus, and the protocol. The last thing, which is forwarding of IP packets. IP address. Yes. So same thing here. We have three interfaces. The concept is that each network is set to an interface. So whenever you see the network, you will know it will go from this interface. Sometimes it have the next hub. So yeah, like here, for example, uh, this address, which is where is it? 65. Yes, here. It will go from interface M2. All right. And there is no next hub. It just directly. We will have 128. Where is it? Yes, 128. It will go from M1, the interface M1, and so on. So each one of them is matched with an interface that will go. It will go from it, and there is no next hub because it's directly connected. And the default will be uh, with the 65. What is it? Yes, this is the default. It will go from M2 also. It will go from M2 and the next hub of it. So in order to reach from here to here, it will it will have to it must go from this IP. So the hub is intermediate hub is this. The default mean like it's the first one. Yes, it's the first one that connects with the internet or the rest of the world. What else? Uh, yes, he's giving you the destination address. So it will ask you if the packet arrives at R1, okay, so it arrives here, and here the destination address is this. How to know the interface? It will do the, what is it? The mask, symbol mask. It will convert this to binary. It will convert each one of these to binary, and it will do AND operation. If it did it with the first one and the output was this, so it's not identical to the address that is giving, so which does not match to the corresponding network address, so it will be discarded. It will do the same thing with the second network address mask. It will do a mask with this one, the original one, and when it did it, it shows like 180, 70, 65, and 120, which correspond to the same as this one that the mask was did for. So which means that it matches to the corresponding network. So it will go for interface M0. So the next interface is M0 are extracted. So whenever you have an IP address, you will do an AND operation between the binaries of the both of them. Whenever it matches the one that you are doing the AND mask with it with the IP address, you will go for its interface and so on. Address aggregation, yeah, same concept as we have seen. Is there anything important here? Next address interface, nothing as I can see. I don't know, just take a look at it. I didn't see anything useful here. Here is the concept says like longest mask matching. So whenever you have a prefix, make it the bigger the prefix, make it at the top, so that it's not confused when you do the, because sometimes like when you do the AND operation, both of them are working fine. So you want to make sure that they are ordered by the how the prefix are. So the longest prefix should be at the top. So suppose that we have this address. If the first mask address at the route was applied, it will give, look, it will give this. So this is correct. So the packet correctly from interface M1 and reaches organization 4. Yes, from M1 it will reach organization 4. But if, however, you weren't correctly making the longest prefix first, if you apply the 24 prefix, which is here, this one, would result in incorrect routing for the packets to R1, which means that also this will work fine. Whenever if you do AND with this, it will give you also this the same one that you are doing AND with, which means you will go for the M1. So it will be mistakenly going packet to R1, because M0 will have to make it to R1, so it is incorrect. But since you are ordering them by the longest mask, like the longest mask stays at first, then the second longest mask stays second, and so on. You won't mistakenly do anything wrong. All right. I hope it's clear. That's it, I guess, for chapter 18.